Hi guys. So today I'm doing my second part of OpenGL talk for the conference. I originally submitted one talk, and when I actually wrote down all the things I wanted to say, I realized I had so much material that they were quite happy to let me split it across two, and that worked out well. So yesterday we did what was basically an introduction to OpenGL, a pretty lightning fast, fairly dry to cover all the topics, but thanks for the guys who stuck with me and we got right through it, and making it back to the next talk today, where I think we'll see hopefully some more interesting things, interesting uses of OpenGL, some of the effects we'll get out of GLKit with very little effort, and some of the tools that are available to us. All right, first we're going to do a little bit of a continuation on what I was talking about yesterday, but we're going to add textures to it. So yesterday we had a look at how we draw triangles, how we applied colour and applied lighting to the scene. The next thing you really want to do to flesh out that basic tool set is to apply textures. So what I'm going to do is switch to the demo app I've got, which helps us just visualize the basics of applying these things to triangles. I've updated that app to add some textures to it. So we see I've got these 8 triangles all being rendered on a flat plane, and you can see that there's an image being applied to those triangles. If I tap on the screen, we animate those into a 3D box, and you can see that I've wrapped this image around the sides of this open box. So that's us applying a texture. We've also got the opportunity to turn our lights on and off so we can see how that interacts with the model. So I'll jump in. I've got some snippets of that code so we can see what we did to apply the textures, the important parts. The first thing we need when we're applying textures is an image itself. So I've got an image here. One I took on my way to WWDC this year. I did a little detour, and this is where we landed in the Grand Canyon, just to have a little bit of a look around, and I took this panorama, so I thought I'd apply that to the box that fit the demo nicely. A recommended detour if you're heading to WW, by the way. So what we do when we apply textures to triangles in OpenGL is we need to map the particular image to where we want it to be mapped on those triangles. In this case, it's simple enough that I think it demonstrates the concept pretty well. At the bottom, we've got our faces of the box all laid out flat. So we've got obviously the 4 faces, and each of those faces is made up of 2 triangles. So we can see those there. And then what we've got, well, we work with vertices. So what we've done for the vertice for each triangle, we map that to a position in our texture. So you can see that the top left is mapped to the top left triangle, and so on. So it's those mapping of positions that we need to tell OpenGL about, and then it and the GPU will do the work of actually sampling the texture and applying that across the face of the triangle for us. So in terms of a little bit of code, there's far less code today than yesterday, so don't worry too much. Just looking at our vertex structure that we use to just help abstract the raw C array that we pass our vertex data in. We've got a float. We've got an array of 3 floats for the position of that vertex, X, Y, Z. Then because we're doing lighting in this scene, we've got an array of 3 values for our normal vector. And then we supply an array of 2 values for our texture coordinate. So that'll be the X and Y position within that texture image of where that vertex will map to that texture image. Then in code, we need to load that texture, or load that image into OpenGL as a texture. Now before GLKit, we used to have to grab a whole bunch of code and do a lot of juggling and fiddly things with loading in the image to UIKit or to core graphics, then manipulating the format of that image to get it into something that OpenGL was happy with, determine things like whether a pre-alpha multiplied and all sorts of things, and do a lot of, understand too much about the process of actually what is inside an image. Thankfully with GLKit, all that goes away. We can throw all that code in the bin, and GLKit will do all the hard work for us. So here we simply load our image into a UI image. There's a few ways to do it, but I've just taken a simple path. Then I create a static dictionary with a couple of options. I'd like OpenGL to generate some mipmaps for me. So mipmaps are basically the GPU will generate some scaled down versions of the image I load in, which is an optimization for when that model's being rendered in the scene. If it's being rendered small enough, it'll use one of the smaller scaled images from that mipmap. I also tell it where the origin of the image is, and then we use what's the class GLKTextureLoader. In this case, we can use GLKTextureLoader texture with CG image, give it the CG image, and that's it. It handles all the rest, loading the image in, converting the formats, creating an OpenGL texture object and all that stuff, and we get back an object representing a sort of pointer to that info. Then we want to apply our texture mapping when we're rendering our 3D model. So again, we can use GLKBaseEffect, which we learned about yesterday. Just as a quick revision, or for anyone who didn't come, GLKBaseEffect is another GLKit abstraction which will basically write our shaders for us. It'll apply all the transforms, the projection transforms and model view matrix transforms. It'll handle the lighting and certainly handle the texture mapping, which we're using in this case. It'll handle 2 texture stages. We're just using one, so we enable one of those stages, texture 2D0, we switch it on, and then all we have to do is give it the OpenGL texture identifier, which is the .name property on that object we got back from GLKTextureLoader. We give it that, and that's basically all we need to do. As long as we're supplying our texture coordinates with our vertex data, they should be mapped for us. So just looking at the part where we actually do our drawing, the GLK view draw in rect, if we're using GLK view controller, which we are. This code is, if you were there yesterday, this code's the same as what we had yesterday. There's no more work to do in the drawing code because it's already been set up. We've already set everything up. GLKBaseEffect will handle the texture mapping in the shader. So I'm not going to review that again, but I'll assume you already know that stuff pretty well by now. So revising our loading of textures, we can use good old GLKTextureLoader to do a lot of the hard work. It can load 2D or cube map textures, and we'll actually talk about cube map textures shortly. It can load these synchronously or asynchronously, and it can load textures from a variety of sources, from files, from URLs, data, or CG images, like in our case. We can ask it to vertically flip the coordinate system for us, and we can also ask it to generate the bitmaps for us. Right, the next thing I'd like to do is show off a couple of the effects that GLKit gives us. Basically gives us a couple of effects for free. So very little code required. We'll have a look at what we can do. I'm going to switch to, I'm going to switch to another little demo app I've written for you guys. And we'll fire that up in the iPad simulator. So what I've got here is our favourite conference logo modelled as a 3D model. We've loaded that in and we're rendering it, and we're applying a sort of very simple animation just to make it wobble around. And we're also rotating the scene, and we're rendering a whole background to our scene. So there's something more there than just kind of just grey or white. So what we're actually doing, the 3D model is basically what we were doing, say, yesterday or even just before, where we just render triangles. There's just a lot more of them now. Not a whole lot more, but a few more. And a 3D modeling program exported those for us, but otherwise it's the same basic code. You just a larger vertex array of data. We've got lighting enabled in the scene, so we've got good sort of depth effect. But the background effect that we get as we rotate around the scene, and we can grab hold of that and spin it if we like, is we're using an effect called a skybox. So a skybox is a technique to give us this 360-degree background to our scene, and it's implemented by basically surrounding our scene in a cube. So it's like we're inside this cube where all sides, all 6 faces of the cube have a texture which is created carefully so that it looks like it encompasses our scene. The other effect we've got available in this little demo is we can turn on reflections, and we get basically what appear to be turn our model into a reflective surface, so it's reflecting the background, from whichever direction, and we get a pretty cool effect there. So that's kind of neat. So I'm showing you these things because GLKit supplies some ways to do this, which takes very little lines of code, so it was quick and easy to show this. So let's have a look at how we can do that. So let's look at the skybox first. GLKit gives us a class called GLKSkyboxEffect. And the first thing we need to do is, to set up this effect, is to give it images for the skybox. So as I said, a skybox is basically a cube, and we just supply 6 images for each face of the cube. And we're supplying effectively the images like we show here. In terms of code, we use our good old friend GLKTextureLoader to actually load them for us. So what we do is we give it an array of the paths to those 6 images that we're going to apply to the skybox. And then we set any options, like we tell it where the origin is. And then we use GLKTextureLoader cubemap with contents of files and give it the array. And it will handle all the work of loading them all in, creating the cubemap OpenGL texture object for us and all that stuff. So in our setup, we create an instance of the GLKSkyboxEffect object. And all we have to give it is the reference to the skybox, to the cube map. So we, again, like before, we pass the OpenGL identifier across to the texture cube map property. And then, just like using, say, GLKBaseEffect, we set the transform and we tell it what the projection matrix is in the model view matrix, so that the skybox is rendered properly in our scene to match the other things we're rendering. Then again, in GLKViewDrawInRect, where we do our actual drawing, like a GLKBaseEffect, we send it the prepare-to-draw method, and that will cause it to create its shaders, compile them and load them in if they're not already, and activate those shaders. One difference to GLKBaseEffect, where we actually do the triangle or the polygon drawing ourselves with something like GLDrawArrays. In this case, SkyboxEffect will do the drawing for us. So it handles setting up the vertices for that skybox, loading them in, and then actually applying the draw. So we just simply call the draw method and it takes care of that. So GLKSkyboxEffect, it manages the vertex data for the skybox that we want to render. It requires a texture cube map that we can create with GLKTextureLoader. And we call prepare to draw to load in its shader, and then we call draw to actually render it out. We don't have to call any OpenGL drawing commands ourselves for that effect. For the reflection effect, we've got another GLKit object, as you'd expect, called GLKReflectionMapEffect. So for this one, GLKReflectionMapEffect is actually a subclass of GLKBaseEffect. So it handles all the same effects that GLKBaseEffect will do, but it adds a sort of reflection mapping texture stage to that, so we get that special effect applied. So as an example, in our setup, we create an instance of GLKReflectionMapEffect probably instead of GLKBaseEffect when we want this effect applied. We enable one of the lights in our case because we'd like to use some lighting. And then we take a different path for setting up how our lighting reacts to our model by setting the material property. So this is an example where we can actually define how the material reacts to the light rather than sort of setting the light properties, which we could also do as well. So I set a few properties of that material in terms of the diffuse color, ambient, and some emissive color in terms of how the material generates sort of a small amount of light-looking emission. And then, similar to the skybox, we pass a cube map to the ReflectionMapEffect's texture cube map. So a reflection map actually takes a cube map as well and uses that to apply the reflection effect. And in our case, because we're reflecting basically the skybox, we'll pass a reference to the same cube map across to the reflection map effect. So that's pretty handy. In our update method, which is called every frame to do our model update before we do the drawing, we set the transform again as we usually do, and then we also set the matrix property to the transform of how we want the reflection map to be applied. So in our case, we sort of just take the current rotation of the scene, inverse and transpose that to get a kind of reflection, the correct matrix for the reflect, and pass that in. And then in our DrawInRect, we do our normal drawing. So prepare to draw, same as with the GLKBaseEffect, and then you would call your GLDraw methods below that, which I haven't bothered to put in here. So the GLKReflectionMapEffect extends the GLKBaseEffect and adds a texturing stage to perform the reflection mapping for us. And to do that, it requires a cube map texture to pass in and a couple of extra properties to set, but very little code, so that's pretty cool. All right, the next thing I'd like to talk about is some of the debugging, profiling, analysis tools that Apple provide. Actually, some really, really awesome tools, especially in Xcode for the debugging. The frame debugger has been invaluable in my learning and understanding how OpenGL works. So we're going to start with that one. What I'm going to do is demo that for you, and I'm going to run that little Swipe 3D app on the iPad. I've got the iPad here just so you can see that it's running, but you don't really have to focus on that. We'll be looking really at the debugger on screen. So, and then I'll show you how we can activate that. So firstly, on the big screen, eyes up, if we can see, focus down to the bottom where my cursor is, on our debugging bar, we've got this extra icon here. And if we mouse over that, it's called Capture OpenGL ES Frame. That's the way we kick off the frame debugger. So if I click that about now, our app pauses, and what it's actually doing is stopping execution of the app. It's running one extra frame and basically grabbing a snapshot of every single thing that happens in that OpenGL frame for that draw call, or actually for that frame. And it's loading them into this funky debugger. So what I'm going to do is just walk through all the things we get with this and what they all mean. So firstly, starting in the middle with the two obvious images of our rendering, on the left we've got what is the color buffer. So basically the buffer that we're drawing into is shown for us on the left, and we see that the hand or the swipe model is being wireframed for us. We can switch that on and off. And on the right, we've got the depth buffer. So if we've enabled depth buffer, we'll get that. If we've enabled any other types of buffers, we'll also see those as well. So we can have the wireframes if we want them, which can be useful. The next thing we'll look at is on the left. We've got, basically in this left panel, we've got all the OpenGL commands that were called during that frame. And I basically mean all of them. So everything called by GLKit as well, within those GLKBaseEffects and any other GLKit conveniences, we see all those things as well. So if I sort of start at the top, we'll notice that our buffers are cleared, and that's because as we can walk through this frame, walk through these commands, and as we choose one, we get reflected for us in the buffers what was being drawn up to that point. So it's a handy way to kind of step through your frame like you're stepping through your code. So we'll sort of skip through this frame and just have a look at that. We've got, we jump to say GL clear, and that's where the buffers are cleared for us. That's cool. We jump down and see there's a lot of sort of configuration state changes. Just to point out where the icons are blue here, they're effectively setting up OpenGL state ready for the next draw call, and these circly ones are where the drawing will actually happen. So the drawing is batched up and sent off to the GPU. So we've selected one of those, and we can see that we've got something drawn. So that's GLKSkyboxEffect actually drawing part of the skybox, so one of those faces of the cube. If we step through some more, we'll probably slowly see more of that. I think it's down here. We should see the rest of the skybox appear. And then following that, there'd be the OpenGL calls to set up the next shader and so on, and then the call to draw our swipe model. So that's extremely handy to walk through and just see, and especially in a more complex scene, what's being drawn, what isn't being drawn, or what's being drawn in front of others. And sometimes the wireframe helps to know where the triangles are actually being drawn in the scene. The next thing I'll do is show you these things on the right. But firstly, while I remembered it, I want to show you the stack. The other thing you can do while walking through these OpenGL calls on the left is if you switch on this stack view on the right, you'll actually see in your code which parts of your code affected, well, caused those draw calls to happen, or caused those OpenGL commands to happen. So here we can see that these are part of the skyboxEffect prepare to draw. These ones are part of the skyboxEffect draw method. Some other ones down here would be the other effect prepare to draw, and then we'll have our actual GL draw elements to do the drawing. So that's also pretty handy. The other thing we get here, which is very handy, is all the OpenGL objects that were currently bound and available for drawing in that frame. So here, if we open this one, we can see we've got a cube map texture, so we can verify that that is actually correct. That's what we were expecting. Oops. We can look at our vertex array objects. Another reason to use vertex array objects is we can actually look at the data that OpenGL is using at that time. We can see it's split into the attributes, so the position and normals are all here, and we can look through all those. We can look at the vertex buffer object, which is effectively just the raw data. If we switch that to floats, we could look at that. If our vertex array objects information wasn't telling us something, we could look at the raw data in that buffer. I'm using index drawing in this case, which is just a technique of reducing duplication in our vertex data and supplying a set of indices for where to draw or where to pick those vertices from, so we can look at that as well. And one of the very cool things is we can actually look at our shader programs that are being used as part of that draw call, including all the shader programs that GLKit generates for us. So this one here where we're using GLKBaseEffect, this is the vertex shader that it generates for us, so we can look through it, basically Apple's code, and see how they're doing those effects and learn from it. So we can look at the vertex shader. So we can see there's actually a fair amount of things going on in these. It looks like they're template generated and they comment things in and out as they need the properties or the effects enabled. And we can switch to the fragment shader and have a look at that. So especially with your own shaders as well, that can be useful to make sure that the correct one's loaded and what was actually going on. And finally, we just have another copy of our render buffer, which we can verify there. Lastly, in this debugger, we've got a bunch of hierarchies at the bottom representing both all the states of the context, so everything that's been switched on and off, and what their configurations are, which can be useful. And here next to that, we've got another view of the bound GL objects. We can look down at the hierarchy to see again, how things were configured, what was enabled, and so on. So we've got a whole heap of tools there to analyze what's going on in a particular frame. Once we're done, we can click continue, and then everything should keep running, and we're back to that. So that's pretty handy. Definitely learn to use that one. Next, we'll have a look at some of the instruments available to us to do some profiling. There's a couple that are there, so let's just quickly have a look at those. If we fire up our profile build on the iPad, and we'll get instruments popping up asking us to choose one, hopefully. In the graphics area for iOS, we've got core animation, which you're probably used to. We've also got two OpenGL ES instruments. So we'll look at the first one, OpenGL ES driver. So if we fire that up, we get the familiar instruments view. We get and the app should be running, we get a time profiler at the bottom, so we can see how much of our CPU is being used for this particular application. That can be more important than you think, because we may have performance problems, which is why we fired up instruments in the first place, and those performance problems could actually be on the CPU side. It could be just the simulations or the physics you're running or some other normal application logic, or it could actually be OpenGL but on the CPU side. If you're doing too much OpenGL state configuration and other things, that can actually cause CPU bound and not GPU bound. On the other hand, if that looks fine, like in this case, we can have a look at the OpenGL ES driver. That's got a couple of properties enabled, which may not be there by default. If not, you can switch to this configuration view, flip that over, and there's a bunch of extra properties hidden in here that you can switch on and off. to see more about the OpenGL statistics. The ones I usually look at first are these utilization ones. So I'll switch on the utilization statistics, enable those, and then we get this data here. Starting, say, on the right, we've got a core animation frames per second. So here we can see the actual frames per second of our rendering. It's called core animation frames per second because OpenGL is rendered to a frame buffer which OpenGL or core animation will ultimately composite and render to the screen, so we're still driven by core animation. So we want that to be 60 if we've asked for 60. Then we've got the utilization statistics here. We've got the Tyler utilization, which is basically equivalent to how much work the vertex shader is doing, or the vertex stage of the pipeline. So here, being 0, there's very little work in the vertex stage of this pipeline. The render utilization effectively tells us how much work's going on in the fragment side, so how much of the pixel filling work is causing, is keeping the GPU busy. And here we've got that amount, not too bad. And device utilization is basically how busy the GPU is overall. So in this case we can see we're basically mostly busy on the fragment shader side of things, but still we have no performance problems, so we wouldn't worry too much about that, I don't think. We'll jump over and have a look at the other instrument, and that's the OpenGL ES analysis instrument. So here we get an OpenGL ES driver instrument again, as that can be useful in this context. But we'll focus on the OpenGL ES analyzer. That gives us a bunch of statistics being graphed here. But down the bottom is where I usually find the more interesting information. And what it does is analyzes how we're using OpenGL, what calls we're making, and compares that against sort of best practices and gives us a bunch of no, 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 you should not do that, or warning, this isn't usually recommended, just check you know what you're doing. So if we look here, we've got only a few things because it's a very simple app. The things, we've got something like this, unnecessary logical buffer store, okay, that could be interesting, but usually you'd focus in on the ones with a lot of total occurrences. So here, this one keeps going up and up, so whatever it's worrying about in this case must be happening every frame. We've got a redundant call, a redundant state call. So we go, okay, what are you talking about here? We can open the right-hand panel and we get this more information on why it's warning us about this particular state. So we'd read that to get an idea, and we also get a stack trace of where that is actually being called from in our code. So this is probably sort of the next step to have a look at, to get just an idea of whether we're doing anything that's for these particular devices isn't recommended or is bad practice for OpenGL. The other tool we've got available is kind of similar, but targets badly performing rendering. It's not actually part of instruments. If we jump into the scheme editor and select a specific profiling tool, we can go down and skip instruments and pick this OpenGL ES Performance Detective. And this is a separate application that ships with Xcode. So we'll pick that. You could also fire it up separately, but I just like to do it this way because then we can just go profile again. So that, instead of calling instruments, that'll fire up the Performance Detective. And this is the one you would use if you've got poor frame rate. So you fire that up, it's waiting for you to click Collect Evidence. You might wait till a particular part of your rendering. Then what it does is similar to the frame debugger, it pauses your app, analyzes what you're doing in or around that frame, and basically just gives you a report of why you're having performance problems. In this case, we're not having any problems. We've got a nicely written app, so it's telling us you're actually really good. You've got no problems here. In fact, you could probably do more drawing or better textures or whatever if you like. You've got some room here. But if you were having some problems, it would give you some tips on what you might look at first. So that's it's probably one to dive into if you've got badly performing drawing. Okay, so we had a look at the OpenGL ES driver instrument and the analyzer instrument, and then we had a quick look at the performance detective and made sure our app was absolutely fine in that respect. So those are the tools that we have available to us. The frame debugger is extremely useful and can help you a lot with understanding what's actually going on under the hood. And then obviously the profiling tools are there when you've got performance issues. The analyzer can be useful for even just checking if maybe you don't have performance issues, but you want to make sure you're doing your OpenGL setup in the correct best practice way. So in terms of best practices and aiming towards performance, I just want to run through a couple of tips that I've learned along the way, so the things that are recommended for these devices in particular. All OpenGL, like I said yesterday, is cross-platform. There's many different devices, many different types of GPUs. All of them have different recommendations and best practices. So we're certainly focused on iOS devices with PowerVR GPUs. So a lot of this comes via the PowerVR guys, and through Apple recommends obviously the same things. The usual recommendation, profile before and after your changes, certainly not OpenGL specific. You would be doing this anyway with any performance analysis. But in terms of OpenGL, a lot of the tips really come down to keeping the data as small and optimized as possible. They're small devices. A lot of the optimizations come from keeping the memory bandwidth utilization as small as you can, as well as keeping the shaders, the actual GPU processing, as underutilized as you can. So once you're processing less data, things are going to be rendered more quickly. And remember that the bottleneck can be typically the easiest places for us to look are in the vertex stage, could be in the fragment stage, or they can certainly be CPU bound. So you'd want to use your profiler to check where your problems are happening. If you've got problems in the vertex side of things, then the sort of things you would be looking to do are using vertex array objects and vertex buffer objects, like I've been talking about. Look at interleaving your vertex data, and look at using triangle strips or triangle fans to reduce the number of vertices. So I haven't really talked much about these, but they're another way to lay out triangle primitives, which helps reduce the replication of vertices in a vertex array. Look them up and see if they can help you. Also consider using element arrays. I touched on that briefly when we were looking at the debugger. This app, which will be available open source, and you'll be able to get that and have a look at how I've put it together, uses element arrays, which are just a technique for if you've got a lot of duplicate vertices in your vertex array, then you might reduce those down to a unique set and use a separate array of indices to refer to those vertices in the array. And sometimes they can reduce the size of your whole vertex data, including the indices, by a significant amount, so they're worth looking at. If your performance problems are more on the fragment side of things, then the first thing you want to look at is the size of your textures, keeping them as small as possible, and remembering that these are small devices and often the 3D models are rendered quite small as well. You can often get away with quite small textures and still get good quality drawing. Also, combining multiple textures into one large texture, which we call texture atlases, can help quite a bit. There's a bit of a performance penalty in the GPU switching textures during draw calls, so we want to reduce that as much as we can. Using mipmaps, like I talked about earlier, to generate scaled down images of a texture so that when it's drawing small versions of it, it only has to pull in the small version of that particular texture and save on memory bandwidth. Also consider using PVR compressed textures. So specific to these particular, like our PowerVR GPUs, the GPU manufacturer recommends a certain format of textures called PVR. These are lossy compressed, but the reason they're useful is that they can be natively decompressed or decoded by the GPU on the fly. And they can compress down quite small, so they're worth looking at. Also, you can consider using lower precision pixel formats. You'd have to test these to make sure you didn't lose enough quality, but sometimes you can gain quite a bit of savings with those. In general, you should look at these tips to try and help performance as a whole. So limiting object modifications to the start and end of a frame. Modifying objects during a draw call or in between draw calls. Because of the way these GPUs function, they actually try and defer as much of the drawing as they can. Even if you submit, draw this object, draw that object, draw that object, they may actually defer all the drawing as late as they can and then submit that through the pipeline, which helps them, the way they tile things up and process as much as they can at once, perform hardware hidden surface removal. That's where they get a lot of their performance with very little power draw. If you're causing that pipeline to be stalled, so it's having to flush through part of the drawing, then flush through another part, you're actually causing a lot of overhead there. So these couple of tips, including avoiding synchronizing and flushing commands, which will flush out the pipeline, and also things like querying the OpenGL ES state or asking OpenGL to bring back data from the buffers. All these things cause the pipeline stalls, which will slow things down. Also, look at using all the cool functions and math types that GLKMath provide. All the GLKMath functions pretty much cover all of the 3D math stuff that we would need, and they're also all optimized to use the Neon vector extensions of the ARM CPU. So and supposedly they're future-proofed, so any other extensions added to these GPUs in newer devices, they're supposed to cover those as well, so we're told. So they're worth using. Throw away any math functions you've brought in, like I had from other code here and there. Might as well use what's out of the box. And of course, profile and test and profile, just keep profiling and you'll eventually get down to some good performance. Some references for performance. So I've just touched on a few things, but I haven't really gone into the depth with those tips. These documentation references here will really fill out the details of why I'm recommending these things better than I can. So Apple's OpenGL ES programming guide for iOS is the first resource you would read front to back, and that fills out a lot of the details. If you are hungry for more information, then you can grab the Power VR docs from the GPU manufacturer. They've got a performance recommendations guide, and then they've got an SGX architecture guide, which is useful to get an understanding of why these recommendations are in place. Last thing I want to show you guys is something that is more of a practical use for OpenGL in a day-to-day application. I don't know, we're probably not all here to do game programming or augmented reality silly apps. You might like to think of how you could use some OpenGL in your normal app that you're aiming to put out to the store. These are just some experiments that I came up with to show how we could potentially use this. So we'll switch apps. We don't need the iPad. So what I've just come up with is a real quick experiment showing how we could use OpenGL to fancy up some of our storyboard Segue transitions. So I've got an oversimplified demo app here that just transitions. It's got a couple of images slapped on just so we've got something to see, and it transitions from a grid of images to a single image and back and forth just so we can play around with these ideas. So I've got 3 ideas here to play with, or 3 experiments. First one is a box transition. So that basically just transitions our scene with a sort of 3D box, spins it around and brings it back, as you can obviously see. Kind of more similar to if you've used iBooks and you switch from the catalogue to the store or the library to the store, that kind of effect. And that's using what we've learnt in these 2 sessions. That's not too hard to do. So that's kind of cool. I've got this one called Tile Fly, where I split up the view into a bunch of tiles and sort of fly them out of the screen towards us. Pretty simple. We could add more effects to that or fly them out in different directions. But that's also fairly simple to do. And the last one I've got, we'll see that once more. Last one I've got, I like that. So people who know me probably don't expect me to do any demos if I haven't tried to ram physics engines in there somewhere. So this one I wanted to experiment with an idea to try and get some cloth physics effects into one of these transitions. So I came up with this one where if we do that, we kind of get this spin around effect and this attempt at almost a cloth thing. Which, with a little bit of time, it didn't take too long to get something working just enough. It's certainly not shippable, I wouldn't think, but even the end transition needs tidying up. But I got there, I got something working in the end. It was a bit of fun. But it's a demonstration, these 3, they're all kind of different effects on, this is how we can actually use OpenGL where the user doesn't need to know that this they don't think this is a 3D game or anything like that, but we can use that to sort of sex up a few of these transitions. I wouldn't say across your whole app, but in certain areas where it might be key. If I've got a couple of minutes left, I just wanted to show you some of the how I did those segue transitions, or just a quick look at some of the important parts of that. So again, this app it's open source, and you're able to grab this after the talk and have a look at how I've done it, have a play with it, pull it apart. Also, I'd be interested in any transition effects you'd come up with, and certainly submit them back if you like, and maybe we've got a repository for silly ideas here. Okay, so we'll just have a quick look at the storyboard for this. So these are using storyboard custom segues. So in our view, I've got a single view controller, and it's segueing back to itself just to keep things nice and straightforward. Each of the buttons causes a segue back to itself, and each segue is set up to be a custom style. So you normally use push or modal if you're a normal coder, but if you want to do something custom, then you pick custom and you tell it what class will be handling that custom segue. So we've given it a class name here. If we have a look at that class, FS Fancy Storyboard Segue, so we've got here's the interface, we've got a subclass of UI Storyboard Segue. So to create custom segues of any kind, you don't have to use OpenGL certainly, this is the technique you use, create a subclass of UI Storyboard Segue. Then we've got a few extra properties, but I'll cover them in a moment. If we switch to the implementation, the only thing you have to do in a custom storyboard segue is to implement the perform method. So when the segue transition is about to occur or ready to occur, your perform method's called, and you can do whatever you want to make that transition happen. So in our case, what we do is we take reference to, so this object gets a source view controller and a destination view controller assigned to it. So we've got access to both the source and destination of our transition. So for what we do with our effect is we grab a reference to the source view controller's view and the destination view controller's view, and we're passing these to a transition view controller. So I'm using an actual view controller itself for each of these OpenGL transitions, and we're telling it what the source view and destination view are so they know what to transition from and transition to. And we'll set ourselves as the delegate of those. So this transition view controller isn't part of the storyboard custom segue stuff, it's just something that we've invented to handle this for us. What we do to kick off the transition is we tell the source view controller to present the destination view controller over the top of it without animation. Then we immediately tell the destination view controller to throw the transition view controller over the top of that, so that we've got the source and the destination, and the transition's actually visible, and it will then perform the visualization of transitioning from the source view to the destination view. Once it's finished, it'll call back the delegate to say, I'm done now, and we simply dismiss that transition view controller, and smoke and mirrors, we're back to we've finished our transition. I've just grabbed one of these, say the box transition view controller, and just give you a quick look at a couple of bits here. You can pretty much see, we're going to look at just a glance through here, so you can pretty much see all the vertex data is the sort of stuff we've been seeing. We've got our vertex data for the faces of the box. We've got the same sort of stuff with view delay. We're using GLK view controllers and GLK views, so there's little code to write to set all that up. One thing I did want to show you though was when we're setting up our OpenGL part of the scene, we create a texture atlas from the source and destination views. So remember, we pass those in as properties to this transition view controller, and when it's setting things up, what it does is it creates one texture atlas containing both the source view and the destination view side by side. So it creates a graphics context, it draws the source view, effectively draws that into the context, then it'll translate and draw the destination view into the same context on the other side, and then load that all into the texture. So then the OpenGL Drawing has access to both the source and destination views, or the as textures, and so it can transition in any way it needs to. And from then on, it's just all the normal stuff we've been seeing, setting up lighting, texturing, loading in our vertex data, and doing all the drawing commands. All right, that's pretty much it. So the demo apps that I've been showing, the triangles one, the Swipe 3D with the logo spinning around, and the fancy Segue stuff, they're all open source and they're in GitHub. You can grab them right now. And that's it. Thanks, guys.
Thank you very much for this working. We've probably got time for one or two questions. The next session starts at 2, and we need to allow time for people to move the room. So there's a couple of questions.
What would you recommend is a good book to start learning OpenGL? And also, is it worth going straight to OpenGL or using something like Unity to do that?
In terms of the book, there's a new one coming out, which I can't remember the name of. Maybe my friend Rob can call it out.
Yeah, let me bring it up.
We'll call that out in a sec. In terms of Unity and OpenGL Direct, it really depends on what you want to do. For something like, say you're trying to do this fancy Segue stuff, bringing in a whole Unity framework is either a lot of work or almost impossible to retrofit it in a normal app for where you're just trying to transition. So this is the sort of thing where OpenGL Raw allows you to get stuff done with very little code. Obviously there's a learning curve, but once you've got it, there's not too much code to actually set it up. Unity, on the other hand, if you're drawing anything quite complex, or even medium complex, then again there's a learning curve for Unity, but you can do complex 3D programming extremely quickly with that. So obviously it depends on your use case, I think is the correct answer.
That book is Learning OpenGL ES for iOS. The author's Eric with a K, Buck.
Learning OpenGL ES for iOS, Eric K.
Buck.
Yeah, and that's just been released, I think, that one, and that covers GLKit, right?
GLKit.
Yeah, so that's probably the one, although I haven't read it, I heard it was coming out a while ago, so that's probably the one I'd look at next. Certainly focus on GLKit for OpenGL. Don't go back to anything horrible before that.
Hi, Chris.
Hmm?
Thanks.
Oh, sorry.
Great talk.
Thanks, Kev.
Notice some magic numbers coming up in there, especially around the shading and the reflective properties and things like that. Where's a good source for that sort of information?
Well, that's another good question. So the question was, you know, where's some good, well, you probably heard it, some good information about how to set up those numbers for lighting effects and reflective effects, the material properties you're probably talking about. I don't have any good recommendations for that, I guess. Well, things like Jeff Lamarche's, his blog covers some of that lighting information in more detail in terms of, because all the lighting you do with GLKit is basically replicated OpenGL ES 1.1 lighting model. So any references that talk about how that works and what the numbers mean and how they applied would be directly applicable to the GLKit lighting model. So I'd say look for that. In terms of where I picked my numbers from, I just fiddled around till I found something that looked nice. And I think that's pretty common with this sort of programming. You might start with something that's very, this is a white light, and then I'll actually tint it this way, apply a bit of emissive property here, and oh, that's a little bit better, that's a little bit worse. So. So that's another really good question in terms of how do we get 3D models into our programming. There's no easy answer, but the way I go about it is to take the simplest path, or a simple path. So from the 3D modeling programs, like your 3ds Studio, or commonly I use the cheap ones like Blender, but more recently Cheetah 3D, which is a $99 3D modeling tool in the App Store, which I highly recommend. You can export to OBJ. And OBJ is a good format because it's simply text and it's easy to parse. I don't recommend parsing that at runtime, but I do use some little tools and there's some Perl scripts available to translate those OBJ files into raw C arrays or a header file of raw C arrays or into a raw data file that you could read in with NS data. And that's the method I use. So in this case, say with the Swipe 3D model, where I just imported it as a header file of floats, I used just a little Perl Python script, whichever one was available, to do that conversion from OBJ. In the future, hopefully, just to answer the question a little bit further, Apple will port SceneKit, which is a framework they've added to OS 10. Hopefully they'll port that to iOS. So on OS 10 now with SceneKit, they have the ability to load collada files into a scene graph directly and manipulate that, including sort of bone structures and animations and all that stuff, which looks really awesome. But we can't do that yet on iOS.